Started. Welcome everybody to think it's our fifth TWed of the spring 2019 season. Tonight, Sabbir Rashid, who's our
halfway grad student,
Tetherless World grad student, is going to talk about the Semantic Data Dictionary with a highlighting resources for using the Semantic Data Dictionary specification and talk through a bit of a tutorial. And the whole point of this is for us to absorb, us to ask questions, have good discussion. The usual heads up, we are streaming live and recording for posterity. These videos are made available via the Tetherless World YouTube channel. And we hear that they're easily found via the Google. So the world will know. So without further ado, take it away, Sabbir. Thank you.
All right, thanks, John. So just a few disclaimers before I begin. So this talk will be informal in the sense that I won't present any of my slides. I'll just go through some of the resources real quick, and then we'll just get going and start working on the tutorial. And I'll run this tutorial as if I don't have any of the software involved. And the reason I'll do this is so that someone who can start from a fresh machine. And the way that I'll do this is by using a vagrant virtual machine. But right, before I get to that, a few disclaimers. So I'll be going over our resource throughout this talk, which is available here. However, this resource is a working draft. So if you notice mistakes in it, please let me know. If there's something that doesn't make sense, let me know. This resource is hosted on GitHub, so you can just leave GitHub issues if you want, or you can tell me directly. Another disclaimer, there's one thing in this tutorial that I'll be covering, which is kind of a convenience thing called templating, which isn't currently part of the Semantic Data Dictionary specification. We submitted a paper on this work last year, and this idea of having your own, to be able to specify the URI that you want to generate was a issue that came up. Another part that's not in the specification that I'll touch upon very briefly is that this code I'll be going over, which is a code to parse semantic data dictionaries. It also has, so I allow the user the ability to use their own properties from semantic web resources to make this code ontology agnostic. So what I mean by this, there's a set of properties in the Semantic Data Dictionary specification that we use by default, but in my interpretation code, you can update that. And I'll touch upon that briefly, but that itself is was to address a reviewer's comment, but it still needs to be reviewed internally before it's part of the specification as a whole. Okay, so without further ado, let me take a seat. And we will begin this tutorial. So just a quick introduction before I begin the tutorial is, so what is a semantic data dictionary? So a lot of people in this room have already seen semantic data dictionaries or the knowledge graphs generated from the script I will describe, or have heard of semantic data dictionaries in some sense. So essentially, Semantic Data Dictionary is an approach developed by the Tetherless World Constellation for creating a knowledge representation of data using best practice ontologies, vocabularies, in such a way that we can create a semantically consistent representation. And we do this by annotating the dataset variables themselves. Furthermore, the Semantic Data Dictionary specification can be used to annotate individual values as well. So by this we mean your data set might have a certain column which is categorical. So like an example from the chair project is education level, right? So there may be different education level values which may be encoded by a number. So the code book of the Semantic Data Dictionary, you can then assign those codes to actual classes and ontologies. And I'll go through this a little bit later. So pretty much where we're getting at is that this approach allows us to both annotate the dataset variables to map them to concepts or multiple concepts in ontologies, as well as dataset values. And this resource that I'm going over is available at tetherless-world.github.io/SDD. I should also mention that the code I'll be going over is available on GitHub as well. And this is just an interpretation code. And let me just share the link. So also on github.com/tetherlessworld/semantic data dictionary, the interpretation code I'll be using is available. And this link is available in the tutorial, and I can point you to it when the time comes. So just some quick logistical things. So the interpretation script I'll be going over was built with Python. I'm using very few libraries, but the important ones are pandas, config parser, and rdflib. So if you want to contribute, maybe study up on these a little bit and contact me directly. We'll be going over the tutorial here, so I'll skip most of this stuff. These semantic data dictionaries are being used by over 10 institutions, or well, over 10 projects across over 5 institutions. So for example, it's being used by Mount Sinai School of Medicine. It was initially being used by Gates through the HBGDKI project. CBiz, when Anna Dyson was here, CBiz experiments were encoded using semantic data dictionaries for the RPI case, pretty much an architectural environmental project. This work has moved to Yale with Ann Dyson, so it's currently being used at Yale. We're also doing some work with N. Haynes in Brazil, as well as some sensor-related work around the Fitbit. So this work is also being used in Brazil. RPI uses this for several projects, including the chair project, N. Haynes, some work we did with N. Haynes. Hales is using this for several projects, and we're also using this for encoding MIT's MIMIC EHR dataset. So the semantic data dictionary approach has been around for the past few years, and it's starting to get some widespread use. So this means that there's a need for quality documentation, tutorials, modeling guidelines, which hopefully you'll agree that what I'm presenting is a starting point for those resources. Right, and so then we go through some code of conduct if you want to contribute. We currently don't have versioning, but we might use something similar to what Y is using. And then we're planning to submit a version of this resource to either ISWIC in the next month or CICKIM, CICKIM, a month after that. So that involves researchers from RPI, University Federales Minas Gerais in Brazil, and Columbia University. And this work's being tested by MSSM. So, and then we'd like to acknowledge the funding that supported work that's been done up to this point on semantic data dictionaries, and that includes NIEHS, the NIH award, IBM research through the AI Horizons Network, Gates Foundation through the HBGDTAI project, and the CAPES Foundation. We'd also acknowledge members of TWC and RPI who've contributed. All right, so before I go to the tutorial, real quick, let me just run through the documentation. I won't go through it in too much detail. So the Semantic Data Dictionary is essentially made up of 5 tables or sheets or Excel file, whatever you want. 5 tabular data formats. The one that ties them all together is the info sheet. So the info sheet is almost like the config file of the Semantic Data Dictionary. And at the very least, it points to the other tables, right? So the other tables are the code mapping tables, the code book tables, the dictionary mapping table, and the timeline table, right? So there's additional updates to the info sheet that are currently on the table, but I won't address here because they haven't been approved internally. But there has been discussion of advancements for this. Okay, so kind of the meat of the Semantic Data Dictionary is the dictionary mapping table. And this is a table that we use to annotate the variables of a data set, right? So these are the column headers in the data set. And we annotate them using several columns. So pretty much the dictionary mapping table is a table that has a column with the columns from the data set in that column. And then we have all these other columns where we can use to assign, to do a semantic mapping. And you'll see an example of this in a second, because here is one. Okay, so here's an example from the chair project that we got permission to use some time ago. This was a while ago, so take it with a grain of salt. Everything I show to you here, take it with a grain of salt. This is a work in progress. But you might have something like, and actually our example will look a little like this, but you might have a column for an ID, a race, age, education level, all these. So these are the actual columns, and then we can assign these actual columns an attribute from an ontology. And we say what is the attribute of. So what makes this approach kind of special is that unlike traditional mapping approaches, the Semantic Data Dictionary method, we're allowed to create annotations for implicit entries that aren't actually in the data set, but we know that is being described by the data set. So there's no column in the data set for subject, right? Or participant or patient or whatever. But we know that this identifier is the identifier of that subject or patient or participant. For chair, this was the identifier of a child. So we can also talk about implicit things that aren't explicitly in the data set, which then we can annotate. So for example, this child is annotated as a scio-human who has the child role in relation to some mother, which is also another implicit entity, and so on and so forth. Then we can also include I guess that's as far as go. We can include provenance information. For example, this BMI was derived from the weight column as well as the height implicit entry. But more on this when we walk through our example. Like I said before, we're also allowed to annotate individual values of the data in the event that they're categorical values. So that's done using the codebook. Here's an example codebook. So you could have like a categorical race column, education level, smoking status, insurance, and the data we see in the data set itself are numerical, but what they're actually encoding are actual classes or categories of things. Another thing we'll touch upon briefly is the timeline. So if we go back to the dictionary mapping, there's this time column, right? So actually, if you look here, we're saying that this education level was the education level of the mother at the second visit. This was the age at the first visit. This was the insurance type. This might be an ad hoc example that doesn't exactly make sense, but so if you have discrete time entries, you can encode them in the timeline, which I'll go in a minute. But you can also encode reference implicit entries that you don't need a timeline for. So for example, there's this birth time point and this pregnancy time point, which we don't include in the timeline and we can just include as an implicit entry, right? So this time, if you go back up here, it maps to SIO exists at. So we're just saying that this measurement exists at this time point, and that's how we encode it. But if we want to get into more detail, like actual dates or how many days or weeks or whatever, the start time, end time, we can then use the timeline table to encode these further and further annotate these. Okay, so at this point, pretty much what we're doing is we're assigning classes from ontologies to concepts in our data set or concepts described by our data set. However, sometimes classes and ontologies are named in such a way that we can remember them. Like the naming convention I see show up here where you have like SIO has start time, that's pretty readable, or SIO human, SIO birthing. These are all readable URIs, which are pretty easy to remember. However, we often have URIs which are not meaningful to the human, which corresponds to somewhat automatically generated URIs, which normally we won't remember. It'd be pretty hard to remember that UO 00000015 corresponds to centimeter. Who remembers that? So what we allow is the inclusion of a code mapping table where we can put shorthand codes that then resolve to the URI, and we can assign it a label as well. So if you see back to the example dictionary mapping, you see for the units, I use SIO year over here, which is a class in an ontology. But for these 3 units, instead of trying to figure out what the UO term was, I can just use the code mapping code, and it'll resolve as if I put the actual URI in there to begin with.
Do those then have in their definition that presumably somewhere we can resolve down to kg?
Yeah, so
that's in the SIO?
No, so for example, this kg is in the code mapping itself. So we create this. We have to specify what we want this code to translate.
No, I understand that, but I'm saying, but this is just intermediary. This is just a link inside the mechanism. The real mapping is the OBO blah 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 9.
Yeah, is there kilogram?
But and the fact that that represents kilogram and there's the notation kg, that's in the OBO definition. That's what I'm asking, right?
Well, so the fact that it represents kilogram is in the OBO, in the UO definition.
Yeah.
However, this code KB that we used isn't necessarily. It might be, but I could have called it king, and whenever I put king in, it resolved to this URI.
Yeah.
Right. So this is custom. It's up to you. Whatever you want, you can specify it however you want. Okay.
So
yeah.
So if you could scroll back up to where you're breaking out the visit, so down. So here it's due to the definition of SIO week that you have to start with, right?
Yeah. So actually, so this is the. Yeah. So the unit of those 4.1 is weeks. So that means 4.7 weeks in relation to conception. So that's why we have in relation to here. This is kind of from the perspective of a child health data set where the mother is visiting the hospital during the first trimester, second trimester, third trimester, or maybe a certain number of weeks after the conception, after the baby was born. So this allows us to encode it relative.
Okay, I actually misinterpreted. It's you're actually creating a new type, which is chair visible units are weak. Okay, so
Yeah, so this becomes encoded as an instance of chair visit, which has a SIO start time and a SIO end time. In SIO has units weeks in relation to the implicit conception entity, which is actually defined back in the dictionary mapping as the conception of the child.
Okay.
Okay, so code mappings. Okay, so this next piece, I'll just talk briefly about. So this is specific to the SDD to RDF Python script we'll be demoing today. Is that we can do a Python any style configuration where we can specify the relevant files, we can specify the locations of the output files, and the two other things we care about are the prefixes we use within our dictionary mapping and codebook and stuff. So for example, over here we use SIO, human, chair, pregnancy. How do we know what that is? Well, this prefixes file, Habitat does something similar as well. But this prefixes file tells us what to resolve all these namespaces to. And then the space URI is the URI we want to assign for the resulting knowledge graph fragment. Okay, so this is what the prefix file looks like. It's just a tabular file with a prefix and a URL. Note that your base URI should also be included in the prefix file. And okay, another disclaimer. So this property customization is not part of the current semantic data dictionary specification. However, in the last paper we submit on this was a complaint by them that if your approach is really ontology agnostic, then why are you dependent on SIO, RDF, RDFS, SCOS, and prog, right? So,
so why are you dependent on the backbone of those?
Well, exactly, right? Which is so these are the default set of.
It's like if it's ontology agnostic, why are you using RDF in there? Why are you using SCOS? Why are you using what everybody uses?
This was a legit. Well, it was mostly about SIO, but because
as we learned.
Well, there's a certain worldview to SIO, which is very nice and concise, but not every worldview aligns with, like the BFO worldview conflicts with SIO. So pretty much the complaint was that maybe someone doesn't want to use SIO. Maybe they want to use their own worldview. How will they do that without having to update the code themselves? Well, so for the interpreter script I'll be going over, we allow them to specify a properties file where they can change any one of these properties to whatever they think is their worldview. However, we're not validating this at this point. It's not part of the SDD specification. So users who do this are recommended to exercise caution and make sure that what they're doing results in a semantically consistent model. So the reason we have this default model is because it results in a semantically consistent model, but we don't want to hold the user to be restricted to this model. But anyways, this will be up for debate internally before we include it in the next revision. And finally, also part of the script which hasn't been approved yet, but also from the kind of feedback we got was this idea of being able to choose your own URIs that you want generated instead of the script generating for you. And this is implemented into SDD to RDF using pretty much the same specifications as R2RML. So the R2RML document is linked there, and I'll actually show an example of this at work very shortly as we're going through the tutorial next. All right, so that was a quick overview. Any questions at this point? Did everything I've said make sense so far? You guys are following along?
So the question I'm gonna ask you later is to clarify that. So scroll on down to your sort of your master, that one, the dictionary mapping.
The example or the specification?
Actually, no, down. That example is to talk about how this is better than
RML, for example, or
the settler script.
It's different.
Well, but
I could split this, add a settler script, and it'd create a knowledge graph for me. So this isn't. It's not like. So what's different?
What I'm saying is, I've seen spreadsheets that are meant to be processed by a settler script that look very, very similar to this.
And actually, I could split this into a settler script, and it'd create a knowledge representation for me. So pretty much Jim McCusker wrote settler code that can take this semantic data dictionary, the set of semantic data dictionary files, and create an ontology of sorts, or a knowledge representation of the dataset variables. So it's not like this approach is does the same thing as settler script does, right? What this does that the settler script doesn't do is, rather than just creating that knowledge representation, it also creates the knowledge graph using the data. So Jim settler script, for example, doesn't use the data to create instances of the graph, right? It just creates the ontology almost.
Okay, I see your point.
Right,
okay.
but
yeah, I see. I see your point.
So everything I've done here can be done using settler. So the reason I did it not using settler is so I can leverage some of the capabilities of Python and just ease of use. But I do also, it can align with settler. And some of the work we're doing in the future, well, we're currently working on, will leverage settler to a greater extent than is being leveraged now. And that's the work that's being done with YIS. Because actually, some version of this code is currently available in YIS. It's an older version, but we're still working on that, right? So Jim will be actively working on that with myself, and one of our URP interns will probably also help work with that. We want everything to align in the end, which was why I was hoping Paulo would be here to see his comments.
Yeah, I'll follow up on that. I don't understand why they're not already meeting at the same place, but I'll follow up.
Yeah. So I guess one motivation of this script being created at all was if we wanted to use semantic data dictionaries, but we didn't want to be constrained to a specific platform that uses semantic data dictionaries like Hatattack or YIS or whatever. If we wanted a stand-alone way to test our semantic data dictionaries, that's what this script is for. So this script, it doesn't rely on any other platform. Okay, so we're almost at the halfway point. So real quick, I'll touch upon the resources, but I won't go into too much detail because this page needs to be updated. So like I mentioned before, Jim McCusker's settler script that can interpret semantic data dictionaries creates a knowledge representation of the data format of the data variables. So we may include some of those knowledge representations as ontologies for the resources that we're publishing. So that'd be for Enhance, for TCGA, and for maybe some non-health data set. But that's not here. This is the source code for the script that I'll be going over today. Well, that will be the focus of the tutorial. So that's this link I showed you before, tetherless world/semantic data dictionary. So this is open source. You guys should all be able to pull this. Okay, so in terms of resources then, actually before I talk about the resources listed, this documentation and the tutorial included in this website are essentially resources, as well as the modeling guideline, the workflow we kind of cover. So those are resources. I'll make that explicit on this page eventually before submitting. But the resources I've included here are actual hand annotated data sets for actual real world data. So we've annotated NHANES demographics data, birth measures data, blood pressure data. To some extent, these dictionary mappings and everything is very rough. Like I said, this website is a month before release. So all this stuff will be cleaned up, but you can click and download these just to take a look. We also include TCGA annotations. So these are the dictionary mappings. We include code books for these data sets. We include the resulting knowledge graph fragments for these data sets. And the reason I'm calling these knowledge graph fragments and not knowledge graphs themselves is one of the motivations behind the semantic data dictionary approach is to ease the whole integration of disparate data sets by using similar annotations and structures, right? So the idea is that we take these annotations for individual data sets, the resulting knowledge graph fragments, which would be part of a bigger integrated knowledge graph. So that's just why I'm calling them fragments, because we see them as pieces of a larger knowledge graph. And then this script also produces example Sparkle queries. So the Sparkle query it produces is just to produce the original data table that was the input, but the structure of the query can be used to get more interesting stuff like the resources in the graph. And we also include pretty much the antecedent to reasoning framework. So these are swirl antecedents. That means that if this is met, then you can assign something to the consequent. And real quick, just so I don't leave you guys hanging, I'll show you what that looks like. So let me just go back down to query and infer. So this is an example. We're going to go through an example. This is the example query that gets automatically generated by the std to RDF script. And this returns the original data. So this is what the original data looks like in terms of this graphical representation. I added a limit here just to narrow the amount of data gets returned. And what I mean by swirl antecedent, this is swirl syntax of the representation that gets created. So this is a subject with an identifier. This is a weight at time point 1, weight at time point 2, so on and so forth. So you can take pieces of this, the whole thing, whatever, to create swirl rules. Unfortunately, I won't be going into that today, but that might go into the paper. Okay, so now I'll stop for questions one more time, and then we'll go through the tutorial. So any questions on the resources? Yes, Jason?
Yeah, so my question is regarding the downstream application of STD, because STD already describes the column headers, the meanings of the column headers. And in order to transform the contents in a spreadsheet or in a relational database into post store, so we need to ingest the data somehow. So, but the STD stuff does not cover that part. So the thing is that if I have STD, all the transformation script that you just talked about, and then how can I leverage it for my next step? So
right,
it's
okay.
still not clear for its downstream application how to reuse the technology, because the data is inside of the spreadsheet in the rows. It's not just in the column headers. So the STD, the output of the STD is a small knowledge graph describing the meaning of each column header. But I want to like transform the data inside the rows, inside each rows into a knowledge graph. So
yes, this is what the script does. So this is what the script does that std2 owl, the settler script, didn't do. And this is what I meant by knowledge graph fragments. So I'll actually show you an example of this.
Okay.
So his question was like, what about the downstream applications of STDs where for example, if there was a relational database, how do we get that data into a knowledge graph form, right? And so I have done this with a relational database called Mimic. It's the MIT Medical Information Mart. It's the EHR records, right? So Mimic consists of 9 different relational tables, right? So my approach is just download those relational databases as tabular tables. So then you have 9 tables, and then you can create 9 different semantic data dictionaries for each table, or you can create a single semantic data dictionary for all the tables. But in either approach, for the I think they're called unique keys in relational scheme. So for the key value, the unique identifier, which is pretty much what links the different relational tables together, as long as you create the same annotation structure, the same structure in the dictionary mapping, this approach results in those disparate data sets to almost automatically be aligned, right? And templating aids this even further, where then we can even align to a specific URI that we want.
Yeah, but what's the foreign steps that you need to transform the?
What's the what steps?
Following step.
So it'd be helpful if you had
Example.
Well, it would be helpful if you had a diagram.
Yes.
You know, it'd be. I mean, for explaining what you're explaining is a workflow, and you know, and answering Jason's question is really easy if you can point at a diagram.
Okay. All right. So let me point out this diagram. So what you're saying is we have this raw data, right? And this raw data might be stored in CSV files. It might be stored in a relational database. And pretty much what we're doing is we're data lifting. We're lifting this raw data to be a more meaningful representation of the data elements. And something that might aid that would be an existing description of the data. So for example, if we're given a data set, how do we know WT means weight in kilograms, right? Usually there's some additional specification, some additional documentation explaining the data, right? So what we're doing here is we're using the raw data and we're using the initial versions of non-semantic data dictionaries or codebooks or whatever to create these semantic data dictionaries, which consist of these 4 different tables. Right? So what's not seen in these arrows is the conversion process. So pretty much what I'm doing is similar to what you were discussing and what Jim does, is that we traverse the dictionary mapping and we have the pretty much representation structure without even looking at the data. In fact, you can run the STD to RDF script without any data and it'll give you the knowledge representation for you. The details of how that's happening is when I do that creation of the knowledge representation, I'm storing everything into tuples or dictionaries in Python. And then I iterate through the data and I go back and pull from the dictionary the specific annotations.
Yeah,
and then
so
I write that
that's
in
what I'm talking about. So for example, for Halatek, so its data injection is based on the STD specification, right? So, but we need to also, we still need to write extra code to inject those data, I mean, in the CSV files into Solr. So I'm wondering if you have any further plan to kind of sort of formalize the data injection process.
Right, I see what you mean. So
can I do a timeout here?
Yeah.
You haven't actually done
the tutorial.
Yeah, why don't you
go through the tutorial?
Why don't you actually do that?
Yeah, and actually, I might, due to lack of time, I might just walk through the tutorial instead of physically doing it. But yeah, so the output of
don't worry about installs and stuff like that.
Right. Yeah. Exactly.
Go
Yeah.
straight to...
Yeah. So the output of this approach is a RDF file, right? So this approach is currently supported by triple stores. So if we want something like Lucene or Elasticsearch querying, we would need to go an extra step, and then maybe we can talk about this together to determine how we'll get there. But yes, maybe it's not the most efficient way to do querying for a system like in Hatattack, which is why Hatattack uses Solr.
But you know, I think Jason's intuition is not off too far, because if you're, like, for example, Elasticsearch, you have this hierarchical structure, this JSON-based nested structure, which you ultimately are going to load in. And you've got all sorts of little, it wants everything broken down in items, right? You got 40 gazillion items that you have to push into that. And this is something that you could conceptually model using this approach and have a script to interpret that correctly. So instead of RDF being the ultimate result of this conversion, you're directing your semantics into a different direction. You're directing it into the serialization that you would have. You would feed into Solr, or you feed into Elasticsearch, which is counterintuitive. I mean, but it's very logical.
Right. Yeah. It uses the same hierarchical model structure.
That's right. It's just a different serialization.
Yeah. So I don't have this functionality, but I want to add. Yeah. I want to add the ability to output different file formats. Like, so I only output trig right now, but maybe you want N3 or turtle or whatever. Maybe you don't want a graph representation. Maybe you want this serialized JSON or whatever. So that would be future work.
Let's see some stuff.
All right. Yeah. So time for the tutorial. So pretty much the setup is how to set up a virtual box. Actually, we might, let me just do it. So I've already set up this virtual box. CD std VM. So all that virtual box is this vagrant. I take a vagrant file, which has this thing. And actually, I've already done vagrant up, but pretty much you do vagrant up to get that vagrant file processed, to get the machine set up, and then vagrant SSH to SSH into it, which I'll do in a minute. So that's what this vagrant file is. Once we bring up the vagrant machine, we want to SSH into it. Just taking a minute. And I also add a little convenience here thing. So when you're using VirtualBox or Vagrant or whatever, you're in an external VM. But sometimes you want to copy over files from your own directory. So pretty much the way you do that is using the mount command. You mount to a shared folder. And this is just adding that mount to an alias, because you end up having to do that mount every time. So let me vagrant SSH. And if I ls the share folder, I see nothing's in there. But if I do this mount share command and ls.share, I see it has everything that was in my VM folder. So I can just copy things over. Okay, so let me just remove, I'll keep that one. Let me just remove this Semantic Data Dictionary folder. Okay, so if you're following along, what you want to do here is pull the Semantic Data Dictionary code. That's simply a git clone github.com/tetherless-world/semantic-data-dictionary.git. All right, so that pulled the latest version of Semantic Data Dictionary code. Okay, so instead of working directly in this Semantic Data Dictionary folder, this is where the code lives. So this is the Python code And this STD to OWL is Jim Sutler code that interprets semantic data dictionaries. So instead of working in this directory, what I usually do is create a working directory. So let's just call this STD workspace. And I'll CD into this workspace. And the first thing I want to do is create a symbolic link to the Python code. And that has to be a relative URL. So what I'm doing is ln-s for symbolic link. I'm going back a directory to the semantic data dictionary directory to the STD to RDF file, and I want that link to be created here. So now if I ls, I have a copy of the STD to RDF file here. So I can just run this from this folder. And just for brevity, I'm going to just copy the example project over as well. So I'm recursively copying the example project here. ls example project. Okay, so I copied over the example project, and let me just run this to make sure everything is working. And the way you run this, this std to RDF script is you specify the config file I was talking about earlier. And this config file does the same thing the info sheet does almost, where it's just pointing to the folder locations. And if you have folder locations in both the config and the info sheet takes precedence. Okay, so I'm running this. Let me do.
This reminds me a lot of CSV to RDF for LOD. Never used that. I used it. You've used it. I did. You ever used it? I don't think you did.
Okay.
You used RDF stuff.
All right. So so I just ran it and I got an error. Module has no attribute namespace. This is an RDF lib thing. So I'm just going to make sure I have RDF lib installed, which I didn't, but it needs some permissions, I guess. Okay. And actually, let me just do, because I installed it with, let me try to run that. It's where this is happening. Anyways, let me just step away from the VM. So that was an old VM. I need to go, there's something weird going on with RDF lib version. But instead of starting over, let me just go to my local version and I'll just run the same thing, std to Python, std to RDF on that example config file. Example project config. Config. Okay, and it worked. So so one thing, we're using RDF lib here, but there's no logger attached to it. So that's why you're seeing this error. That's not a problem. If I put this into Flask, that error would go away. But right now it's a standalone, so ignore that error if you see it. So real quick, before I go into too much detail, let me go into this example project and I'll go into the output and just show you what was generated. So there's 3 folders here. So a Sparkle query was generated, a swirl antecedent was generated, and the trig file was generated. So the Sparkle query is pretty small, and it's the example I showed before, which is cat sparkle example query. It's that same example, automatically generated based on the structure of the semantic data dictionary. Swirl, same exact thing. So if I cat the swirl, I see that swirl representation, which then I could do something like this implies I have a NHANES, let's say NHANES, say I have a class called NHANES patient like this, which is, so I can imply that this subject is an NHANES patient. For example, right, I can write inference rules. I won't go into too much detail right there. But finally, the meat of it is the actual output, right? That's what you guys all came to see. This is what Jason came to see. So let me try to zoom in real quick. Let's make that size 16. Select. Okay. All right. Bigger? Very well.
Even bigger, huh?
Okay. Yeah, for those of you following along in the video, this might be fine for you. But we're also projecting this on using a projector. So that's better. Okay. Yeah, I'll post this RDF in the documentation. So so pretty much what gets created is a nanopub format. I won't get too much detail into the head, but what we're doing is the pretty much each of the variables are OWL class is created, which is a subclass of what they were annotated with. In the actual formal semantics forms of these restrictions are like using OWL restrictions. The settler script does this, but my script doesn't do this yet. But this is just a basic representation. But what we care about is the actual knowledge graph. So for example, where is this? This is here's an example assertion. So we have the ID is an instance of is RDF type identifier is the identifier of this first subject, and it has a value of 1. And then we have the weight at time point visit 1, the weight at time point visit 2. Those visits are encoded over here. So for example, visit 1 is a chair visit, which has a start time with a certain value and an end time with a certain value and a certain unit. So the time point is encoded here. And then we have these explicit entries, right? So these are the actual columns of the data set represented. These are actually individual values in the data set. Represented as RDF, and then we also have this implicit subject being represented as well.
Why don't you have some of these? Why don't you have SIO as a prefix?
For where?
Flash or no? Yeah, at the bottom of race 4 or any of these.
Why are those expanded?
Why don't you have prefixes for those to make it a little bit easier?
Like RDF-S is a prefix
right.
over here.
You've got prefixes elsewhere.
Yeah, this is an artifact of RDF-lib. But
well, the other thing is kind of funky is you've got
the prefixes with the triangle brackets.
Yeah,
that resolves fine. So because like when you look at this synth form here, right, this internally resolves to this before it resolves to this, or it resolves to this inside this, and then when some RDF parser sees 2 triangle brackets next to each other, it turns into 1 triangle bracket. It's the same thing. They both.
But yet you got, that's kind of funky because that means you can't take this. Okay.
Yeah, so the serialization isn't really important. I mean, whether we're expanding URLs or not. So just from the use of RDF-lib, it likes the expanded URLs more. It's hard to. RDF-lib expands everything you print through RDF-lib expands it out to the full resource. Regardless.
Okay, so you're assuming that RDF-lib is going to.
Well, so the whole.
What I'm concerned about is if you were to, so this is a trig file. It's not a.
Okay.
It's not turtle.
Right. So we have 3 minutes, just enough time to load this in. So I'm going to just run BlazeGraph. There's documentation on, or the tutorial includes how to get BlazeGraph up. So I'll just copy this URL where it's running.
So while you're doing that, I think the answer to my question is we're looking at trig and not looking at turtle.
Right. But I mean, Turtle itself could have the URIs resolved either, and Trig itself could have the shorthand notation either. I'm on your page where I like to see the short stuff better, but RDF-lib is the de facto standard right now. Anyways, so I'm in BlazeGraph. I'm gonna do a update, and it loads, so it is valid RDF. And for the query, I'm gonna just literally copy that query I had. Let me just pull it from the tutorial.
In the same directory, you could just.
I could just cat it and.
You had it right there.
Yeah, it's right here. So let me just copy this. And what's also nice about the automatically generated Sparkle query is you don't have to go search for all your prefixes again. It's just a convenience thing. All this was done for convenience. Okay, so let me just spit out that query. And then you see you get the data back in this kind of form, way 1, way 2. There's a little bit of a bug with the time. So that's why you're seeing some of these being repeated. But this just kind of gives you the first step. So like, what if I want more information, right? What if I want to actually see the subject? So then we can add the subject to the query as well. So then we see which subject it's about. You can go and explore it. You see what attributes it has, age, sex, whatever. You can do whatever you can with a BlazeGraph endpoint. So there are still at least one bug in this, which is why there's multiple things. But if I did the same thing without a timeline, the bug wouldn't be there. So it's a bug in the interpretation of timelines. But I'll be addressing that before the next month. But regardless, so what we have here is a way, but we can see a lot. So pretty much anything in this query is like, so subject V, visit to V, race E, sex E, all these things are actual URIs in the graph. And this naming convention I'm using for Sparkle, V stands for virtual or implicit entries, like the subject, and E stands for explicit, like race. So then we can even see the race and go in further. This race 7 is unknown race. This guy didn't know their race. But how about this one? This race 4 is American Indian or Alaska Native, you know? And this actually came from the codebook. So this is a demonstration of how the codebook ends up resolving into the graph itself and assigning those classes.
I think that's a very good point. The example, so when you were looking at that trig file, you were looking at a codebook value that's based on a codebook. And what you saw there, I mean, you made the side comment, this is a nano publication that's representing this. The initial impression is that this is kind of a bogusly long way to represent a value, right?
Yeah.
But what you were representing is something that's a lot more subtle than just a value. It's a value from a codebook.
Yeah, exactly. It's a code value, and that's why it has a type associated with it as well, right? So there's so if anyone here went to Jim's talk on the predicates, Eugene, on
Be
not
careful with that predicate.
Yeah, on not overusing predicates. So pretty much this representation uses a fixed set of predicates specified in that properties file. Let me go over here. So actually, this representation, you can write software using only these predicates, and you can traverse everything in the graph. And even better yet, kind of in line with Jim's discussion, or actually it's a SIO model, the only data type property here is SIO has value. So wherever you see SIO has value, it points to the data value. Everything else points to objects or annotations. So it's a very concise model, which is what's kind of neat about this, where to write code that leverages this, and we have done this for the poster that's not up here anymore, the breast cancer work, you kind of know what properties you need to expect based on this model.
So you have sort of this interesting issue that, so Jim's talking, you're talking, kind of good bookends. Okay?
Mm-hmm.
This, to do things right, using and making things reduced to sensible first principles like this,
Mm-hmm.
okay, requires a certain structure and a certain discipline to do that. You need something like the Semantic Data Dictionary specification and the tools that go with it to do that.
Yeah,
right?
to organize it for you.
Right, yeah, you need that in order for it to be tractable and not to go crazy.
Right.
And not to have errors, which is more important.
Mm-hmm.
You need that sort of
representation, and then you can use whatever interpretation, be it settler, be it STD to RDF, be it head attack. If you have this representation organized in this way, it's a kind of generic mapping that then software that's written using these properties can, it doesn't, these are three different tools that all use a singular format.
So, and now the answer to my question I asked towards the beginning that I'd said, why don't you just do it? They're using settler.
Mm-hmm.
Well, the answer is you would end up hard coding
exactly
code,
yeah,
the rules that you're sort of doing a adjustable way with this.
Mm-hmm.
So you could, yes, you can write settler code that'll take a look at it, convert tables and do the right things with your variables.
Mm-hmm.
But it would be hard coded settler code to do all of that.
Exactly, and because settler's kind of, I mean, settler in some sense is built off of Ginger and Python, but in another sense is its own language. I mean, it's its own syntax in the sense where settler, the input to settler is RDF. So anything you can do in RDF, you can't do. Well, it's hard. Maybe there's workarounds using the Ginger, but this lets us use the full Python power.
But I think though that Tim Lieber would probably say he could do this with CSV to RDF for LOD too.
Right. So, and which is
there were two of us in the room. That were still in the room who would know how to do that.
yeah.
So,
but from what I've heard, and I haven't looked into too much detail for myself, you need to be somewhat of a computer scientist to use CSV to RDF for LOD.
I don't know. What do you think? I'm not sure.
Whereas we've had non-computer scientists, epidemiologists use this approach successfully.
So we have people doing that are not specialists, right? I'm not sure if they have a completely easy time doing it.
So you configure CSV to RDF for LOD and Turtle. Okay. So you're configuring it in Turtle. So you're piloting it with that. The workflow is you point it at your table that your CSV that you're going to convert,
mm-hmm.
and it can convert some real monsters. It creates a raw file.
Mm-hmm.
Then so it's basically a template. Okay, so it's like this is what I found, and here are the places for you to go to town. Then you pop in and you set what your predicates are going to be. In essence, all the columns that it found, what those assignments are going to end up being. So for a simple file, a simple CSV, it's actually very quick. It's because you almost have it.
Mm-hmm.
It even has the possibility of creating refined versions of the conversion.
Oh, yes.
So we use like void, if I'm not mistaken,
yes.
to generate versions of a conversion from the original CSV file to the RDF representation. So we have one generation, then we have the refined version, and they're all linked back to the original one.
And it can shout out to other resources as well. You can embed, or it actually will do a query. So as it's going through and doing its conversion, it can actually, what's it called? Link the,
I don't know.
yeah, I think Tim, you watching? But so it can actually, you can embed little queries that facilitate the conversions. But it gets geometrically complex as you try to do more with it.
Yeah.
It's not obvious how you would do, for example, the hierarchies that you would encode in the mapping and stuff. That becomes harder. It'll do time series, which it shouldn't do at all. It should just assume that you have tidy data.
Right. And I think the SDD motivation should be focused on to act like a framework or something like an specification that you can just implement that, or I don't know, use as a model for your data system.
Yes.
So the representation or the metadata for some data set can be specified in that, and it exists in spite of the system you are ingested data to. So that's a good thing, guys. So
I think to really, so it's often true that to really nail these things, that you generalize them. And so if you think, if my target is not simply RDF, but if my target is going to be, say, different kinds of serializations, internal serialization, an Elasticsearch load, a Solr load, these different things which require, they're similar outputs, but they're different serialization forms that require certain abstractions. If you think of the Semantic Data Dictionary as a front end to that, to get that modeling right, and leaving the end serialization is kind of an exercise based on what it produces, then it becomes really sweet, because then it's doing something that nothing else is doing, because that's a really hard problem. Is here's my data, but here's my target. I'm just citing Elasticsearch because I've gone through a lot of things.
So my question is like, what extra business logic should be right above the SDD specification to get the data ingested? So I
More
check
Python code.
further check the contents that the data table that you show us. I want to check what's missing if we ingest, because ideally, so if this framework is fully reusable, and then we can actually apply it directly in Habitat. We don't, because for now we have the measurement generator to write complex business logics to ingest the every DA files.
We use a subset of the SDD specification right now, and we would do stuff on that subset in order to work for Habitat, right?
Yeah,
so all the SDD specification, we use a subset of it with additional things to.
Right.
So we're at almost
over time.
So what I'm going to do is I'm
hang
going
up.
to ask for us. Thanks,
Thanks, everyone.
And then I'm going to stop the broadcast.